So we've been doing area, so now we're going to start doing volume. So the idea is pretty straightforward in that when we had area, what we did, just to recap real quickly, you have these two curves and you go, okay, I'm going to figure out what the height of that is, right? And then multiply by the width dx. Okay? What's happening here is instead of having just something that's flat, we have something that's three-dimensional. And what's typically going to happen is instead of this being the whole thing, this is going to be like the footprint, or like if you've ever looked at floor plans or blueprints or something like that, you're seeing what's on the ground, right? And so that's going to be the bottom of it. And then something is going to be coming up out of your paper towards you, right? And I have colleagues who spend weeks teaching their children how to understand what this looks like in three dimensions. I couldn't care any less, right? And the reason is you don't need to know, you don't need to be able to picture it in three dimensions. Now, is that helpful if you're going to be an engineer? Probably. Okay, learning how to visualize things in 3D. Is it helpful for solving the problem? Maybe a little, but actually not all that much, because what we're going to do is this is going to be the bottom of some cross section. Maybe it's a side of a square, maybe it's the diameter of a semicircle. It'll be some part of the cross section. And what we really need to know is here we multiplied this height by dx. Here what we're going to do is we're going to take a slice like this and we're going to multiply the area of that slice by dx to get a little small slice of volume. Like think about it as you have a loaf of bread and you've sliced it into lots of little slices. We're going to find the volume of that slice and then add all those volumes together. That's what the integral will do for us. So here's the basic idea. The volume of a solid of known integrable cross-sectional area, A of x, from x equals a to x equals b, is the integral of a from a to b. That is, volume is the integral from a to b of the area in terms of x. Here are some typical cross sections. A square, everybody's good with that. Rectangle, people are typically good with that. Triangle, yep. Equilateral triangle, some of you may have forgotten that one. It comes up from time to time. We did this one in honors geometry. Part of the reason we do it in honors geometry is because I know it comes up in calculus. It's side squared times the square root of 3 over 4. A circle, everybody's good with that. A semicircle, and this is the typical formula that people use for a semicircle. Let me suggest to you that what's frequently going to happen is if this cross section is a semicircle, this isn't the radius of the semicircle, it's the diameter. So a better formula is if I replace the radius with d over 2, I get a is equal to 1/2 pi times d over 2 squared. And then if you square that and then simplify, you get what I think is the better formula, and that's 1/8 of pi d squared. And it's just easier to do that. Some people will go ahead and they're like, oh, this is the formula I know, and they'll put the diameter over 2, but frequently people forget to square it, square the denominator, it becomes a mess. This one we'll get to a little bit later. This is an annulus. And you're like, what the heck is an annulus? Well, think of a washer. It's a circle within a circle. And we're trying to find the area in between the two circles. There's a radius, which is the distance from the center to the smaller circle. We'll call that little r. And big R will be the distance from the center to the larger circle. And if you think about it, to find the area of that, it's just the area of the big circle minus the area of the little circle. We're just taking that one little piece out. These two we'll primarily use in the next lesson, which is on volumes of revolution. When you spin something around, you usually get either a circle or an annulus. Today, on this lesson, we're just going to be doing solids where they tell you what the cross-section is. So, the base of a solid is the region R enclosed by the graphs of y equals 2 sine x and y equals x in the first quadrant. Each cross-section cut perpendicular to the x-axis is a square. Find the volume of the solid. Okay, anytime you mix trig functions with polynomial functions, it's almost always a calculator problem. In fact, all of these are pretty much always calculator problems on the AP exam. Every now and then they'll put one on the non-calculator, but they'll just ask you to set it up. They don't want you to be spending 10 minutes going through a really, awful looking integral. So, let me grab my calculator. Gotta wake it up. And I almost already have it. It's 2 sine of x. 2 sine of x. Delete this junk off of there. And I'll go back to a zoom trig. So there's y is equal to 2 sine of x. And there's y is equal to x. It looks a lot like the one that we had just a moment ago. And so typically what I do is that I'll go ahead and, even if I'm doing this on a calculator, a lot of times I'll sketch a really quick graph. I don't want to spend a long time on that. And it says if I take a cross-section perpendicular to the x-axis, so that means I'm slicing this way, which is sort of the normal way to slice ever since we started doing Riemann sums. It says the cross-section is a square. The question is, so this is the bottom of the object. What's coming up at you, if I slice it, we're going to get a square. Okay, again, not super important that you can fully visualize this in 3 dimensions. The question, though, is what part of the square is that?
Did you say bottom?
Yeah, so it's just one of the sides of the square. So this is just S. So, and I don't always do all of these steps, I mean, just to be bluntly honest, but this is the process that you're going through mentally. So the area for my cross-section is side squared. Make sure you have the right area. Now I need the area in terms of x. Well, in order to get that, I need to know what is this distance at any place that I slice. Well, S is going to be the difference between these two. So that's going to be 2 sine of x minus x, because it's the distance between those two curves. So 2 sine of x minus x. So the area in terms of x is 2 sine x minus x quantity squared. So then our volume will be the integral, and we'll worry about the limits of integration in just a moment, of the area, 2 sine x minus x quantity squared dx. I think it's pretty clear that they intersect at the origin. The other point of intersection, not so clear. So I'll go back to my calculator and go, okay, find me that point of intersection. And I'm just going to move it over here. I'm not even going to guess today. 1.895, yada, yada, yada. And I usually go ahead and put the ellipses after the 5 to show I'm keeping more decimal places than this. I'm not rounding yet. So then on the calculator, I'm going to quit out of my graph. And I'll do a math 9 to get an integral from 0 to, you're like, oh, wait a minute, we didn't write down all the decimals. But remember, your calculator keeps that value in X until you do something else. And since I only needed to keep one of them, I don't need to bother with storing anything. And then it's just a matter of, all right, I need to have 2 sine of X minus X quantity squared with respect to X. And you get 0.456. Questions about that one? All right, let's take a look at this one. Find the volume of the solid whose base is the region in the xy plane bounded by the graphs of y equals x squared and y equals 8 minus x squared, and whose cross sections perpendicular to the x-axis are semicircles with diameter in the xy plane. Okay. This is probably one that you could be asked to do by hand. So let's see. Y equals x squared, just your regular old parabola. Y equals 8 minus x squared. Same parabola flipped over and moved up 8 spaces. So this is, I just take a typical cross section someplace. What part of the semicircle is that going to be?
Diameter.
It's the diameter of the semicircle. So my area is pi over 8 d squared, where the diameter is going to be the distance between these two. So it's the upper curve minus the lower curve. So that's 8 minus x squared minus x squared, or 8 minus 2x squared. So the area in terms of x is pi over 8 times the quantity 8 minus 2x squared. Once we have an area formula, we can go on to the volume. The volume, and we're going to deal with those limits of integration in just a second, is going to be the integral of pi over 8, 8 minus 2x squared dx. And I think you can see why I don't always write out all of those steps. But that is what I think about every single time. And it's not a bad idea to write them out. Yeah.
Is it the whole quantity squared?
Oh, I'm sorry. I forgot to square this. Thank you. All right, so we need to find the limits of integration. So if I'm doing this by hand, I need to find, well, where is 8 minus x squared equal to x squared? So that would be 8 equals 2x squared. So 4 is x squared. Oh, hey, nice. This is going to go from -2 to +2. Just in the interest of time for today, I'm not going to go ahead and solve that by hand, but I think you can see that it's not terrible. I will do the next step which would be, I'm going to factor out the pi over 8 because I hate it. -2 to 2. And I need to square that. So that's going to be 64 minus, that'll be 32x squared plus 4x to the 4th dx. And then it's a very straightforward integrand to take. I don't normally do this, but because the numbers are so large, I might factor a 4 out of everything, or I might multiply through by the 1/8, just to cut the numbers down to size a little bit if I was doing it by hand. All right, let's look at one more of these. So here, let S be the region in the first quadrant bounded by the graphs of y equals x squared, y is equal to 4, and the y-axis. All right, so this has 3 boundaries as opposed to 2, so we're going to have to think about that. S is the base of a solid in which every cross-section perpendicular to the y-axis is a rectangle whose height is 6 times its base. Find the volume of the solid. All right, so y equals x squared, your basic parabola. I always make mine go up too fast. Y equals 4 is just a horizontal line up here someplace. And the y-axis. All right. So they could have told us that this was in the first quadrant, and it would have had the same effect. Here's where this one's a little different. It says every cross-section perpendicular to the y-axis. Okay, so my cross-sections are going this way. So because my cross-sections are going this way, I need to have everything as x in terms of y instead of y in terms of x. So this is going to be, if I solve this equation for x, well, one side is the negative square root of y, the other one is the positive square root of y, and since this is the first quadrant, this is the positive square root of y. And this side over here is x equals 0. So first of all, my area is going to be base times height, where the height is 6 times the base. So that's base times 6 times the base, or 6b squared. This is the base of my rectangle. And at any slice that I take perpendicular to the y-axis, it's going to be always look at right minus left, bigger minus smaller. So that's going to be the square root of y minus 0, which is just the square root of y. So the area in terms of y is 6 square root of y squared. It's just 6y. So our volume will be the integral of 6y dy. Every now and then these come out to be really, really nice like that. What will my limits of integration be? Well, the least y is down here. That's 0. And what's the maximum y? 4. This one is really nicely set up so that you can, slice it perpendicular to the y-axis rather than perpendicular to the x-axis. So that's going to be 3y squared from 0 to 4 is 48. Okay? All right, so the next sheet you have is tonight's homework, but the sheet after that is about volumes of revolution, and I want to get at least partway through this today, and we still have another, I don't know, 10 minutes or so. So the idea here is that instead of having like this static object, like a building or something that is weird, what we're going to do here is we're going to rotate our region in the XY plane around some line. We will only do this around horizontal and vertical lines. We won't do these around lines that are at an angle, because that gets really, really difficult. What you end up having to do if the line is at an angle is you end up having to do a whole nother system where your X and Y axis aren't horizontal and vertical, they're running parallel or perpendicular to that line. It gets a little mind-blowing. We're not going to do that. Okay? So we're going to revolve the region about a line to create a three-dimensional solid. The cross sections of these are either going to be a circle or an annulus. And here are the two different types. If the axis of revolution is one of the borders of your region, then when you spin this around, if you think about it like this, with my pen, my finger is the axis of revolution, this pen is my cross section. When I spin it around, and I'll show you this way, when I spin it around, it sweeps out a circle, right? And this is going to be the radius of the circle. So that when I spin it around, it spins around like this. And you don't have to necessarily, visualize this, but that's basically what's going on. You end up with this circle. I've tried to sort of give you the three dimensions. You can actually do it if you do your axes at an angle, and you can, anyway. I used to be really good at doing that. I've stopped doing it because it's not worth the time. Now here, the axis of revolution is somewhere that's not a border of the region. So here when you spin this around, I'm spinning it around, so notice when I take my pen and I spin it around, it's still making this circular motion, but there's a gap. You're going to have an annulus. When I spin this around, the other half is going to come all the way down here, like this. And I'm going to have, that's going to be the gap in the middle. And this will be the other part. So it sort of looks like a CD, right? Or a Blu-ray disc where there's this hole in the middle of it. Okay, so if your axis of revolution is a border, your cross-section is a circle. And after that, it's exactly like the slices that we just did. Okay? And the same for an annulus. Once you know that the cross-section is an annulus, then you're like, okay, I just need to find all the pieces to fill into my formula. On this one, I didn't write them in. This is going to be your little radius. And that is the big radius. All right. So let's do an example. Find the volume of the solid formed by revolving the region bounded by the x-axis, the graph of y equals the square root of x, and the line x equals 4 about the x-axis. So I immediately notice that my axis of revolution and one of the borders are in fact the same. So I know my cross-section is going to be a circle. So I'm going to sketch a very quick graph. So the graph of y equals the square root of x is the top half of a sideways parabola. The line x equals 4 is a vertical line going to 4 here, and the x-axis. So I usually kind of go over my borders just so, like, this is the part that I'm interested in. And to indicate where the axis of revolution is, I draw a thing that looks like this, and people are like, is that a G? I'm like, no, that's like it's spinning around that. So if I take a little piece here, again, notice that every single one of my cross sections is going to touch the axis of revolution. So that's going to be the radius of the circle. So my area is pi times the radius squared, where the radius is going to be this distance from y equals the square root of x to the x-axis, which is y equals 0. If you'll always think about those as being two functions, it's always the greater function minus the lesser function. So that's going to be the square root of x minus 0, which is just the square root of x. So then the area in terms of x is going to be pi square root of x squared is just pi x. And again, this is one where somebody was like, yeah, we're going to make this so that this is easy to do by hand. So then the volume is going to be pi, I'll go ahead and factoring that out, times the integral, we'll do the limits of integration of just a second, of x dx. What will my limits of integration be?
0 to 4.
Yeah, from 0 to 4. This would be pi times 1/2 x squared from 0 to 4. So that's 8 pi. Okay, I think that's far enough. So how much time do we still have? 37. We got 5 minutes. Let's do this one because it involves this one. So revolve the region from the previous example about the horizontal line y equals 3. So now I'm revolving it around this horizontal line up here. I'm just going to add that onto the graph, y equals 3. And I'm going to do my work up here just because I have the space for it. You're welcome to do it. I would do it down here. But now, do I have a circle anymore when I spin that around? No, because there's a gap between my slice and my axis of revolution. And that gap is going to give me the radius. And this is y equals 3. So my area is going to be pi times the big radius squared minus pi times the little radius squared, where the big radius will be the distance from the axis of revolution all the way to the far side of my representative slice. What's the difference, the distance between these two?
3.
It's always 3. Big R is always 3. Little r is going to be the distance from my axis of revolution to the nearer side of my representative slice. What will that be?
Square root of x.
I'm sorry?
Is it 3 minus the square root of x?
Yeah, 3 minus the square root of x, because it's the distance between them. So then the area in terms of x is going to be, well, that's going to be 9 pi minus pi times 3 minus the square root of x quantity squared. And since we're probably doing this one by hand, let's go ahead and work that out. This is going to be minus, let's see, that's going to be 9 pi minus 6 pi square root of x plus pi x. And you can see that this one was cooked up nicely because the 9 pi's drop out. So that's going to be negative 6 pi square root of x plus pi x. So my volume will be the integral from 0 to 4 of, I'm going to go ahead and factor out a pi, negative 6x to the 1/2 plus x dx. Okay, but and part of the reason this stuff drives me crazy with what some of my colleagues do is they treat these like these are two entirely different things. And like they're really the same thing. You just have to figure out what the cross section is on a volume of revolution, whereas in the volumes by slicing it gives you what the cross section is. All right, y'all have a great day.